So Will, you're there?
Hi, Neil. I can see and hear you loud and clear. How about you?
Excellent, excellent. Forgive my background. Just this follows me wherever I go, so you just happen to catch me, still.
It's both artistically and scientifically appropriate.
I'll say, by the way, it's one of my favorite works of art, not only because it's cosmically themed, but it's clearly not what he saw, because the sky doesn't really look like that, but it's definitely what he felt when he saw the sky. And I think the combination of what you feel and what motivates you and what is what makes us human. And so when I see artists bringing a perspective that wasn't there before, I embrace it. By the way, I think that's what engineers do, but in a different way. Engineers, they say to themselves, gee, there's this little bit of physics over here, or chemistry or biology, and we have this need over here, because you actually can't expect the scientist to do that, because we're just sort of in the lab. Somebody's got to go out there and say, I'm going to take that and apply it and then transform the world. And that takes a certain audacity of creativity that the best engineers have, and society benefits from it entirely.
I think it's a great way to just tee up that there is a real art in science. They're both creative endeavors, and that you're building with fundamental laws of physics and science. You're building with applying them in engineering, and of course, artists build with their own medium, including Van Gogh behind you. But Neil, I just want to thank you on behalf of the Air Force, and I can say Space Force, so I should update my bio. We are so excited that you are willing to join us for this quantum accelerator. And what we're trying to do is make quantum real. It's been talked about. It's a buzzword in the Pentagon. Most people don't know a lot about it. And it's always the future with a capital F. And we'd like to make it the future with a lowercase f. And so we're really delighted that you're going to share your expertise and just your enthusiasm for science in general. And I want to see if you'd be willing just to start by just explaining quantum to the layman. I know that we've got a lot of experts, but I think sometimes hearing something a different way can spark new ideas, even for seasoned veterans of quantum science. So if you would, tell us what you think of. How do you explain quantum when someone on the street grabs you and says, hey, Neil, you don't know me, but I need to understand this spooky law of physics. How do I think about it?
Yeah, so first of all, probably most of who is on this webinar would be way more fluent in quantum physics than I am. I mean, I know quantum physics because I studied it in school, but I don't do it professionally. But what I can tell you, and what I do a lot of thinking about, is what role quantum has played in our lives in ways that people, I think, don't suspect. And let me go all the way back to the Big Bang for the moment. Okay? So let's just start there, okay? That's a good place to start any conversation, I think. But just consider that the triumphs of Newtonian gravity, giving us an understanding of planetary systems and galaxies and the large-scale universe. But then Einstein comes along and says, by the way, Newtonian gravity has limits of applicability. It actually fails at the edges of where Isaac Newton had experienced in his lifetime. What's the fastest thing he would have known? It's a running horse, perhaps. All right. And so Einstein doesn't replace Newton. It extends the understanding of gravity to regimes that didn't otherwise manifest in Newton's formulations of gravity. So of course, when you put low speeds and low gravity in Einstein's equations, you get Newton's, they've come out for free, right? So that's why it's not a replacement, it's an extension. All right, so here we go. So now we've got cosmology derived from Einstein's general theory of relativity, principally. And it's working. We got the expanding universe, we get an understanding of the history, throw some thermodynamics in there. The universe was hotter, okay, in the past. We got this. But then we realize, wait a minute, if you keep going all the way back, the universe was smaller and smaller and smaller and smaller and smaller. There's a point where the universe was on the scale in size of atoms, okay, particles. Well, we have a formalism to understand the behavior of matter on such small scales. That was developed primarily in the 1920s, and it's called quantum physics. Back then it was called quantum mechanics, okay? Quantum physics is the whole thing. So, fine, I don't have a problem with that, all right? By the way, the 1920s was a watershed decade at least from where I see the universe, in cosmic discovery, because that's when Hubble, the man, not the telescope, discovered that our galaxy was not the only one in the universe. There are island universes out there, other galaxies. And it was discovered that the universe was expanding. And we got to apply Einstein's general theory of relativity, and quantum physics was developed. All that happened in the 1920s, okay? An under-heralded fact about that decade, and I'll get back to that in a minute. So here's what happens. The universe is small, and now quantum physics is the most successful theory ever put forth about the behavior of nature. Just want to make that clear. Yes, general relativity is successful, but it has its limits. All right, just the way Newton had its limits, general relativity has its limits. What are those limits? Well, what's happening at the center of a black hole? There's a singularity there, okay? You're dividing by zero in some equations. So there are issues. Well, things are really small there. Maybe we've hit the limits of Einstein's theory, and we have to then invoke this other theory that has never been shown to be wrong, and that's quantum physics. So quantum physics, married to general relativity, gives us an attempt to understand the very earliest moments in the universe. It's kind of a shotgun marriage between these two, the quantum theory and the theory of general relativity. All right, and it turns out, as stated, they don't make nice in the sandbox. General relativity requires space to be smooth and continuous. Quantum physics tells us that on the smallest scale, the Planck scale, space is discontinuous. They don't work together. All right. So you need somebody to come in like you, Dr. Roper, a string theorist, to come in and say, let me perform this marriage in some way that is amicable. All right. Is there a third understanding that encompasses those two? Point is, we have no understanding of the birth of the universe without dipping our toes, our whole feet, our body into quantum physics. Well, let's keep going. 100 years ago, we're trying to understand where energy comes from. So, excuse me, where the elements come from in the universe. There are big, heavy elements out there. Where do they come from? Maybe fusion. You could do that. Well, where would the fusion take place? Well, the space is pretty empty and cold. You're not going to have fusion there. How about the centers of stars? All right, we did the freaking calculation. Okay, you get the pressure, it's gas, there are gas laws, you know thermodynamics, you go down there, you get the pressure, and you find out it's about 10 million degrees, plus or minus. Now you go back into what you learned about protons that are resisting each other because they have the same charge, and you find out that's not hot enough to slam protons together. It's not. You're not fusing particles in the centers of stars, because we know it has to be about 10 million degrees, and we know how particles interact because of their electromagnetic repulsion. So this was a dilemma until quantum physics. And then we realized, oh my gosh, the proton is not just this particle, it's a wave function, all right? And the wave function occupies more than just the spot of the particle. Part of the wave function occupies and overlaps the position of the other proton. And there's a finite likelihood that that proton can find itself close enough to the other proton. That happens. And you calculate what rate that is, lo and behold, you have thermonuclear fusion in the sun because of quantum mechanical tunneling. Tunneling. Oh my gosh, who ordered that? Okay. This is stuff that has no classical analog. And so here we are, bit by bit and piece by piece, assembling an understanding of the universe, which for the longest while, we had no idea was being touched by an entire other branch of physics. Even something as simple as magnetism, something's been known for centuries, okay, has has no understanding without an understanding of quantum physics. And then other phenomena arise, of course, as you move forward. We have superconductivity. All right, who ordered that? You need an understanding of quantum physics for that. Superfluidity. It goes on and on and on and on and on. And so it leaves you wondering, given how fertile quantum physics is in its weirdness and its oddities. It's only weird and odd, by the way, because we evolved in a classical world. Okay, you don't see quantum phenomenon because we can't. All right, so we don't have any intuitive sense of how quantum physics unfolds. So we have to learn it with an equation. Or is that what matter does under those conditions? I guess I got to just keep thinking about that, because I don't have a life experience to hand it to me. The way I drop an apple and I'd let go of an apple and it falls. That's intuitive. Quantum is not, but you all know this, okay? I just want to emphasize how many unexplained, unexplored, uninvented things are out there because quantum physics underpins what's going on. Well, I'm sorry, I'm hogging all the time here. Will, sorry. You asked a simple question, and I just got all in your face.
My friend. Look, I am ready to go back into research. So if you'd like, take over this job for me.
No, we need you. Somebody's got to allocate. Somebody's got to see the big picture, so you stay right where you are. Okay.
It is rare for scientists to be in these jobs. And so I cannot tell you how much I use a technical background to try to help the military harness some of this new science and engineering that it does seem obscure to the person on the street. We don't have an intuition because there's no evolutionary advantage for having an instinct for quantum physics. And most of the things that we experience as waves in the physical world, we can just treat classically as waves. We don't have to deal with the fact that quantum waves like to be waves, but sometimes not. And when I'm asked by people like, when are we going to see quantum effects in the military? I tell them, you already got them. There are quantum effects everywhere. You had a great one that really did change my view of the world when I was a young student, that you just can't get magnetism without quantum effects. You can start zooming into those lodestones that have been discovered by primitive peoples throughout history. They have weird properties. Metals behave differently, but if you need to understand them, you start zooming in, you're eventually going to have to get down to those little microscopic magnetic moments. And for certain metals, they don't sum up to zero. You can get circuits that leave the moment, and you just can't get there classically.
By the way, just it's one thing to understand something and then you feel good about having learned it. It's another thing to say, wait a minute, now that I have that understanding, I can exploit it in this way not previously imagined. For example, so happened to be my physics professor in college discovered nuclear magnetic resonance. All right, and this is it's a peculiar phenomenon, as is everything in quantum physics. But if you have an atomic nucleus and you put a very strong magnetic field across it, if there's a magnetic moment in it, it will align, and you keep it that way. And then you put a varying magnetic field on it, and if you tune it, you can find a resonance with that nucleus, and that resonance actually is detectable. And so that's kind of interesting. It's kind of, initially it would be just kind of like a curiosity. Well, all right, no, you don't expect physicists to do this, but now comes the engineer. Okay, the physicist lays it out. By the way, he won the Nobel Prize for that discovery. All right, so nuclear magnetic resonance. So what happens? A clever engineer says, wait a minute, if you can distinguish this nucleus from that nucleus, because they have different resonances, maybe I can make a cavity and put you in that cavity and distinguish the nuclei of different tissues that comprise your body. Tissues that would not show up in an X-ray, which is famously good for finding your bones, but not much else, okay? Or other calcified things in your body. So thus gets invented the magnetic resonance imager, the MRI. It's really a nuclear magnetic resonance imager, but that's one of the illegal N words in society, nuclear. So they remove the word nuclear from the machine, and it's just now MRI, so you can walk right into it and get this measured. Point is, again, it's an exploitation of a quantum effect that is, yeah, now I understand magnetism. By the way, nuclei can get magnetized in a quantum way, and now it is arguably the most potent machine in a medical portfolio for diagnosing the condition of your body without cutting you open. So here you have this whole community of people tuned into this webinar who are applying, who are invoking their creative brain juices to try to do something that hasn't been done before, exploiting the quantum. And I'm just saying that the day has only just dawned on this topic. And yeah, you want to turn quantum capital future into lowercase future, just turn it into the present. Okay, forget the future, it's in the present. All right. And one other thing before I yield the floor back to you is, you have people today who are saying, I don't need to know this. Why do I need to know? Why do I need to explore space? Why do I need these people who are sort of technology, science and technology skeptics, let's call them. Presumably no one on this call is that, but you certainly know people who are. We all do. These are the same people, by the way, who are rejecting the discoveries of scientists but they're still using their smartphone. Okay. Wait, I got to call grandma. Wait, I need instructions to the nearest Starbucks. Okay. I don't like space. Don't spend money on space. You are finding Starbucks because a satellite is giving you coordinates. Just wake up to this. Okay. I know I'm screaming at all y'all because you're the wrong person for me to be screaming at, but I'm just trying to say that if you were around in the 1920s and you're allocating budgets and you're one of these skeptics, you might say, why are you studying the atom? It's so small you can't even see it. It's got properties we don't even care about. I'm a carpenter. All I care is that my wood atoms cut with my saw. All right. Why are you do this? Is a waste of money. This is some of the most brilliant people in the world dedicated to something that has nothing to do with anything in this world. You know, people today, if they were alive back then, would be saying that to those scientists. Yeah, it would take decades, okay, 40, 50 years especially, before quantum physics would become manifest in the storage, the creation, storage, and retrieval of information. And so then, you know, back then computers are used by businesses, scientists, that's it. The public is still not thinking about it. Now, you cannot wake up in the morning without being touched by a computer in some way or another, and there is no creation, storage, and retrieval of information without an understanding of the quantum. And the IT role in today's economy, I've done some calculations on this, and there are ways to play with the numbers, but a conservative estimate is that IT drives the creation of at least one third of all the world's wealth. IT. And 40 years ago, would you have even imagined that? There are people employed in branches of our economy that would not have existed back then. So all I'm saying is sky's the limit. And I get to say that because I'm an astrophysicist.
That's right. I love that there's no lid on the sky as long as you let the air get really thin. So Neil, I think you make a great point. It's one we've got to get across the military, is that we already have quantum effects. We have them in our personal lives. I think if you didn't understand a lot about physics, if you owned phones way back in the day and saw the progression to smartphones, where you can now store all of the information that would have taken an entire PC, you can now carry around in your pocket. That to be able to store something that's that big and something that small, you've got to get down into the physics of small things. And you know, for the Air Force and Space Force, you know, we run past the fact we're building hypersonic weapons. We'll test one this year, and the black body radiation that will be significant from something moving that fast, and some really cool physics to explore. But you can't understand that without a knowledge of quantum physics and quantum science. And even the laser, you know, is just so common now. We've got laser pointers. We built high energy lasers in the military. And certainly you can't even begin to talk about coherence, the quantum coherence, without having a sense of how atoms behave individually under quantum mechanics.
Yeah, a quick thing about the laser.
I think we have it, to your point. We have it.
A quick thing, if you look up laser, if you Google it, you'll find out that it was invented, in the 1960s or late 50s. I forgot exactly when. And there's also a maser, a microwave amplification by the stimulated emission of radiation. If you didn't otherwise know, laser was an acronym, the light amplification by the stimulated emission of radiation. What's interesting to me is you typically don't, in those articles, don't go back to what enabled the invention in the first place. And it was a research paper by Albert Einstein. Had this particular research paper that I'm referencing been the only thing he contributed in this world, he would be he'd be listed among the most brilliant scientists of the 20th century. Okay. He wrote a paper, I forgot the exact title. It's something on the stimulated emission of radiation. Okay. Okay. And he runs through the calculations and he shows that, that you can, an excited atom will de-excite, emitting a photon. In so doing, the electron changes energy states, emitting a photon, get that, I understand. But you realize that if you bathe this atom in the energy of the same photon that was emitted, it emits more photons. Who ordered that? Somehow the atom likes it, is stimulated by it, and emits more. And so this was a curious phenomenon. It's a quantum phenomenon, a curious phenomenon that would not be exploited into a laser for decades. And Einstein is not thinking, this is the future of barcodes or skin peels, or, it's just, so I think what I'd like to do with your audience here is, I don't need to tell you to get excited about quantum, but because you already are, you wouldn't be on this call. But there are people out there who don't understand it and don't know why they should. And to the extent that I can feed you ways that you can reach them to get them to say to themselves, yeah, technology matters. Yeah, technology is a future. Can I give a quick anecdote here? This will sound like a cheap plug, but it actually isn't. My most recent book is called Letters from an Astrophysicist. It's a compilation of correspondence I've had over the decades with random general public asking me stuff about life, about aliens, about God, about education, about, so it's a compilation called Letters from an Astrophysicist. I just got notice that it's going to be translated into Portuguese for sale in Brazil. The Brazilian publisher wrote me a letter and said, for this edition, could you please write a letter, your own letter, to Brazilians? And I said, why? Because they knew that I know that Brazil has the third largest, if they still do, last I checked, the third largest aerospace industry in the world. If you ask most people in the world, what's Brazil known for? They'll talk about coffee, soccer, beaches, tanning creams, whatever. And somehow technology doesn't come up. Meanwhile, there's a shift in their politics and in their government and in their ways where science is being less valued compared with other things that have immediate gratification. So they see this as an opportunity to get me to say something to the country, to say, look, you already have this. Embraer, you already got something going here, all right? And if you want to be a part of the future, if you want to be a player in the future, you've got to continue to invest in that way. Otherwise, the world will leave you behind. I'm ready to write that letter. I'm going to write it this weekend, in fact. So other countries are thinking about this. Oh, and by the way, you talk about quantum in the military. You like to know that the military is ahead of whatever you're doing. Otherwise, what are we paying for? You guys got all the deep pockets here.
Wait a second. No tough questions here, Neil.
I just remember, when the fastest computer in the world was a thing that would make headlines. It doesn't much make headlines anymore, but the fastest computer in the world was always in the military. Cray computer, Cray XMP, military bought the first one off the assembly line. And so now you don't hear much of that. We know the frontier of that is going to be quantum computing. Personally, I think some of it is oversold in terms of what it would be able to do. Add that to, for example, when they know each other.
Entanglement?
Entanglement, thank you. Quantum entanglement.
Hey, we're ready for charades.
Charade. Yeah, I worked, right? It succeeded.
It sounds like.
So look at quantum entanglement. I think some of the promise there is overstated, about it being a way of faster than light communicating. Oh, by the way, tunneling and quantum entanglement, when you collapse the wave function, it happens instantaneously, faster than light. Quantum tunneling is faster than light. So this is all basically faster than light phenomenon, all right? So there are people very excited about possibly exploiting this. I think, I don't mind people sort of overthinking it, because then you want to go where you've never been before, even if you have to pull back. But all I can say is, if you look at quantum entanglement and say, where are all the records being set and who's doing all the research, the United States does not show up. So maybe we are doing all that research and it's all classified and it's not getting published, or we are stuck at the table and everybody else is in the lab. Okay, China has the record for the longest distance between two entangled particles. It's 1,200 kilometers, the width of China, beamed by two coherent particles that came down from a satellite. Okay, so they got a whole branch working on this. Do we? If we do, it's top secret and nobody knows about it. But I don't, sorry, Will Roper, I don't have that much confidence. Other than what you're trying to do for the military, I don't have the confidence that I can sit quietly at night knowing we got top people working on stuff that needs to be worked on. Just look around the world and you see where everyone else is putting their resources, and that's a sign. And by the way, again, I'm talking too much here, but I just want you to, I don't know what people dialing in from all around the world. Let me just say something about the United States of America, okay? Our self-image is one where, we're leaders and we're this and we're that. And it's because we've actually sort of readjusted the arc of history so that we feel comfortable saying that. But let's take a look at space for a moment, okay? Here's what happened, all right? Russia puts up Sputnik, it's USSR, puts up Sputnik. First artificial satellite in space. We freak out, okay? We create NASA a year and a day later, okay? All right, what else happens? Russia puts up the first non-human animal, Laika, okay, the dog. Russia puts up the first human. Russia puts up the first woman. Russia puts up the first dark-skinned person. It was a Cuban, okay? Russia puts up the first space station. Russia makes the first docking. Russia does all of this, okay? We put someone on the moon and we say, we win. Okay, so what I want to impress upon you is, yeah, we, as a country, we can get anything done we want. But my read of history tells me that we do so reactively rather than proactively, okay? We're really good saying, uh-oh, I have to catch up. Really good at that because we're embarrassed, all right? So somewhere in there, somebody's got to turn that into things we do that are proactive. That's how you truly lead the world.
Neil, my hope is, I think you made a great point. I hope is by doing events like this Quantum Accelerator, just pushing $1 million into basic research, that we are being proactive, but I would say we're being proactive in our reactive response. and that arc of history,
proactively reactive. That's what you're saying.
Meaning we are just so accustomed to being reactive. This is actually closer to the proactive side scale. We're not waiting for something to be on fire before we send in the team to put it out.
Okay, I'll agree with you there. You're being proactively reactive. Yes.
It's like a Led Zeppelin. It's just wonderful to have those oxymorons in our language. But the loss of the Soviet Union.
Wait, you can't let that go. Hold on. So the group Led Zeppelin, when they first performed, there's a lot of screaming in their songs back when screaming was uncommon. Now it's everybody does it. And their music was not like listening to the Kingston Trio. It was hard to listen to for early people, and it then brought everyone else to it, and it became norm. And now it's in the canon of classic rock. When they were first heard, was it by an agent or by a record producer? They said, this music is terrible. If we publish it, it would sink like a Led Zeppelin. So they said, we'll call ourselves that. So there you have it. So I didn't want that to go by unless people didn't know that little bit of history there.
No, I think all transformative music is universally hated by the status quo at this time.
Yeah, that's the force that transforms everyone and brings them to it.
And then when their kids love it, right, then it becomes the next thing. But, for kids growing up today, just thinking back to what it would have been like to have the Soviet Union as a strategic competitor, that is ancient history. For people joining the Air Force and Space Force now, the sense of we're in a competition and it's not clear who's going to win is a foreign idea because of what you just discussed. We presume that we're going to be ahead and leading and dominant. And today's world, that is not a fait accompli.
Yeah, just to put
that I think the military really lost something when the Soviet Union collapsed. We lost the need to compete in all domains, including fundamental science. And so fortunately, we're now feeling we're now feeling that we really need to compete. And there are many nations like China that you mentioned. It's not clear what our relationship will be long-term, but we can't assume the best. We have to plan for the worst, and we can hope for the best, but we can't assume it. And science is an area of competition, and the military can actually play a really valuable role, which is what we're trying to do here. I think what hurt us was that quantum effects like the laser and black body radiation and medical, they actually got bypassed when the impact of the quantum computer on breaking encryption was first raised. This idea that a quantum computer could take all of the trusted communications that the military has and just open them to an adversary that could process with a quantum computer something that all the computers in the world would take longer than the whole history of humanity to churn through. That was a scary thought. And so it started our engagement in quantum computing. And if you look back, it was a naive pursuit that we had camps that jumped into particular trapped ions or optical quantum computers. And that we focused on that for so long that we ran past other quantum effects that now appear to be closer to coming into the military than quantum computing, which was the initial thing that lit us on fire. Quantum encryption is here. So you mentioned the Chinese, the MESIAs, being able to beam down entangled particles, entangled photons, being able to communicate. Well, maybe we don't have to worry about quantum computers breaking encryption if we can use quantum encryption to be secure against a mega computer focused at us. And quantum sensing gets very little hype in the military. And I think it's just a fantastic area to encourage fundamental research. Now, I don't know what part of quantum mechanics is going to be most easily mechanized. I do like that we call it quantum mechanics, because it does provide a new apparatus, a new set of machinery to start thinking about building things from an engineering perspective. And for those who think quantum energy levels are the place to begin, or superposition states or entanglement, which you mentioned earlier, so many different mechanisms to think about new kinds of machines that have never existed before and will likely do different things. And I'm hoping that in this event we do today, we don't just become synonymous with quantum computing, though I did bring one of our research labs, quantum processors, here. I can now hold one in my hand when they used to take up an entire research lab. but quantum sensing, like quantum gravimeters, which could have a variety of commercial uses. You could imagine how the future could be radically different if you could detect an enemy submarine, this big, heavy thing that is below, or how having, say, quantum metrology on a chip, being able to do things we currently do with GPS to navigate. You mentioned going to Starbucks using GPS satellites. Just a small number of Space Force operators operating that constellation. I don't think many people know the military provides that as a free service. And yes, we do have to take into account general relativity to keep the GPS constellation operating with all the leap seconds and small changes that sidereal time just doesn't really jive with the way the world really wants to turn versus how atoms actually emit radiation. So we're already leveraging physics that in the 1920s was so far, and it's now common and mechanized, and quantum isn't to the same degree. And so what I'm hoping that we will do is kind of come back and baseline the military and say, do we have to worry about quantum computing? Yes, we do. There's no telling what they could do, but I'm in your camp. It's not clear to me that a quantum computer is going to be doing better cat videos on a phone anytime soon. But as leading researchers can determine how to write code, computer code, using quantum mechanical language, superposition states, other things, so that a process in the end generates information that is actionable by a military or anyone. Until that's commonplace, there are other things to explore. And I'm curious, out of all of those things, so quantum computing, quantum sensing, quantum encryption, where do you see the application to military problems? And if you were going to place a bet, what would you bet on first for giving us that next quantum effect that we leverage?
So a couple of things. First, I never pretended to be, see the future. And I have very good evidence why you should never trust me for seeing the future. I'm old enough to remember Star Trek in first run in the 1960s. And there they were with these warp drives and photon torpedoes. And I said, yeah, that's the future. Yeah, yeah. And they had this box in the wall where you put food in it and seconds later it comes out hot. Yeah, I can, maybe that could happen. I'm saying all of this. And then there they are walking up to doors that automatically open and close. And I say, how does the door know? That'll never happen. So there I am, embracing photon torpedoes and not even imagining that a door could know that you're walking. People don't know. There was a day where you actually had to open all your own doors, right? And then they got a little clever and they had a pressure pad. You step on that and that would open it. But now, okay, I'm just saying, I don't trust any of my predictions. What I will do, I do a lot of reading of history, however, and I want to give a historical example just by analogy. Are you familiar with the great Manure catastrophe? Have you ever heard of that?
I haven't, but I do work in a government apparatus that often generates them.
Okay, fine. We'll see if you still have your job tomorrow after this. So Manhattan, where I live, it's an island connected by many tunnels and bridges to the rest of the world. It's not very large. It's about 13 miles long and about 3 miles wide. So it's a long, skinny island. You go back 120 years, there were horses that took you everywhere. You either walked or you hired a cab, which was a horse-drawn cab. Okay. There's not only that, all supplies. It's a mercantile mecca. Okay, so horses are pulling everything. All right, horses pull the fire engines. Horses, so horses are everywhere, and they're pooping everywhere. So there is manure everywhere in the streets, and it's attracting flies, and it's a sanitation problem. And so the local government's saying, how are we going to fix this? Well, maybe we can get the chemists to work on and the biologists to work on a feed where they don't have to poop as much, where they process it more into their metabolism. Okay, that might have helped. How about this other thing that makes it less interesting to flies, because flies became the secondary health problem. So all this research is going on. And by the way, they ran the calculation and they said, if the population of Manhattan goes up and the manure continues to grow, because there was a system of removal, you take it from here and you put it over there, where then big trucks, horse-drawn trucks, would then load it up and then take it out of the borough, okay? But what happened was people did the calculation and they said there's a limit beyond which the effort to remove the manure requires as many horses as the manure that's getting laid down in the street. So it's called the Great Manure Catastrophe. And there's all these people working on that problem. And you know what solved the problem? The car, the internal combustion engine car. My point is, you can become so focused on a problem that you are blind to other solutions that are vast. Of course, car had its own issues, okay, including safety before we had stoplights, and then pollution and all the rest of that. But that solved the manure problem without ever having to think about manure. And the manure was not what motivated Carl Benz for perfecting the internal combustion engine, okay? So as you approach these problems, stay broad, because maybe some other solution to another problem renders your entire exercise obsolete. Here's everybody trying to solve the encryption problem. What's the acronym? The three-letter abbreviation, the
AES encryption or RSA encryption?
RSA encryption, okay? So that's the gold standard, okay? We use it because we don't know how to decrypt it in a timeline of civilization. Does that mean that's the only encryption out there? It's the best one we know of now. Maybe to work on a different encryption, okay? That does not then lend itself to the quantum solution that will perhaps come down the pike one day, all right? Is that the only way you're gonna move information back and forth? Find another way to do it. Rendering the interception of information obsolete. Maybe there's so I'm just saying, stay wide open. By the way, contests such as this that you're sponsoring here are just that sort of thing. You're crowdsourcing innovation.
I think the advice is a good one. History certainly supports your position that if you decide to buy a crystal ball, it's just going to be an ornament in your house. And I also take the caution from you that if fundamental science and broad research is our #2 priority, then we will inherit a manure problem of one kind or another. And
I didn't think to take the analogy that far, but if you want to generalize, you don't want a manure catastrophe in the military, right?
It would have been fun to calculate that break-even point of where you cannot add another horse without needing more horses to care for it. And I think your point about exploring broad things, we could get over.
Wait, I got to interrupt. Wait, so on the subject of horses, can you do something about this, please? If you're gonna, with the Space Force, and you got a thing now, I am tired of reading about rocket propulsion in units of horsepower. Okay, no number of horses will ever ascend Earth's surface. Okay, so don't. Okay, can we evolve past horses in measuring this? Okay, I get it that you measure engines in horsepower, car engines, because cars replace horses. So that was something people kind of understood. But cars don't fly. They're still going horizontally. They're still going forward. So if you have any influence on the Space Force, get people to come up with some other measure of the thrust of a rocket. Okay?
I'll take that one on, Neil. Although I do remember as a student, a lot of weird physics problems where you assumed a perfectly spherical cow. So maybe a very well jumping horse perhaps could get us into space.
Cool.
But
Pegasus.
I like your
Pegasus units. How about that?
Pegasus units. I like, of course, they need to fly. So I don't know how we're going to get outside the atmosphere.
Oh yeah, that gets into the atmosphere. So Pegasus rocket power. Yeah.
We need a purely impulsive.
No, you're always one step behind, right? So units of flying then inform the units of space. See, as units of horses, inform the units of cars. By the way, we had the same problem, challenge with nuclear power. How do you tell someone what is the energy of this bomb? Well, they give it in terms of TNT, right? And now you got million tons of TNT, and the units just, they lose their relevance to the magnitude of what is going on at hand.
We could, I mean, since a horse can't get into space, if we could use manure units, because you could burn it, turn it into energy, right?
Oh.
We keep it all in the family that way.
So horses can still look with pride on how they influence civilization.
Yes, they're the actual propulsion on land, and they're generating the fuel for air and space.
There you go. There you go. I have one more historical point I just want to leave you guys with. It has to do with the Industrial Revolution. So we think of it as this great time, you know, you read the history books, and we're still a little bit of it, but it's mostly an information revolution, of course. The Industrial Revolution, most people, I don't think much about what enabled it. Was it just a bunch of creative people? Yes, you need that, but it's necessary but not sufficient to make this happen. What was going on was physicists were figuring out what energy is, how to represent it, how it manifests, how to convert it from one form to another. This was unknown in the time of Newton. As brilliant as Newton was, you read all his stuff, energy is not a thing that he's working with, okay? Because it wasn't formulated yet. That's early 1700s, late 1600s. You fast forward up into the 1800s, people are figuring out, wait, there's energy going on. I'm boring my cannon with this drill, and the drill is getting hot. In fact, it's boiling the water. How did that happen? Mechanical energy is becoming thermal energy. What's going on? Can I measure this? How much is there? Can I convert it? As the laws of physics and thermodynamics arose, in tandem, clever engineers exploited it. And therein was the transformation of civilization. And the years since quantum physics have, you know, it's been 100 years. And okay, we've only begun to exploit the quantum, but think of the quantum in modern times as energy in the olden days of the 1800s. And look at what it did for civilization over a relatively short period of time, 150 years, transformed us. So think of us at the birth of a revolution, of our understanding of, by the way, and a caution here, it's a fun caution, a caution nonetheless, the Industrial Revolution was still based on classical physics, still based on physics that you had some intuition of how it would work. Quantum physics, you can't just sit in an armchair and take your life experience and come up with a discovery, because your life experience is irrelevant. Leave it, check it at the coat check, okay? And walk in afresh. You know what you can do? Imagine that the value of Planck's constant is 1 billion times larger than it currently is. Then put yourself in that world. If you walk through a doorway, you would diffract. Okay? There'd be fun things happen. Okay? In fact, somebody invented quantum chess. Okay, look it up online. You all probably know this. Quantum chess. And you can't actually physically build that board because it involves superpositions of states of the pieces that you're moving. And so each piece has a binary manifestation, but of two different pieces, but you don't know it until you touch it. Then its wave function collapses, then it's one of those two pieces. But once you've touched it, you have to move it. It's a fun, interesting rules. So there's a whole gaming industry, you can imagine, that would be exploiting the rules of the quantum, which are all fun, and they're spooky only because they're not in our life experience, but they're completely natural to the quantum laws of physics.
I might be able to win at quantum chess. Now, as long as I don't look, I really can't be in checkmate, can I? I am with some probability less than 1.
And you have to acknowledge that you're in checkmate in order to lose the game. Is that how you?
That's first rule to working in the government, is always look for the bright side. So Neil, I think the thing we're hoping to do is really within the Air Force and Space Force, and I will take on that. Why are we doing rocket power to space? So for all tuning in, if you've got an idea about how to measure it, these are the kinds of things, though, I think that do make people think differently. Why are we still measuring something with an antiquated system that actually can't achieve the domain in which we're flying, that is space? But I hope
I serve on a recently conceived board of the Pentagon, the Defense Innovation Board, and
we first met.
Oh, that's right, and we are we're tackling. We issue reports back to the Secretary of Defense or anyone who asks in the Pentagon. But we, to the extent that quantum matters, we're there for you to help get that through. Whatever, I don't know if it's still called red tape, but whatever bureaucratic inertia, resistive inertia rather than propellant inertia exists out there. So I'm on your side here.
I appreciate it, Neil, and I'll definitely take you up on that. What I hope that we'll get out of this event are a lot of ideas that are spooky, though we shouldn't call the science spooky anymore. I hope that we get some things that our investment creates new areas of research, new phenomenology. But I also want to provide the connection to where the science can transition into engineering. We start by being educated in simple machines, the lever, the wheel, the pulley, but quantum mechanics provides some very new machines that have no analog into the machines that built the Industrial Revolution or the physics that undergirded it. And so I know that if we don't get the engineers, the appliers involved, that the demand and resource that we need to keep putting into fundamental science is easy to let up on, because the pragmatist of the world, you're only one potential leadership change away from having a pragmatist in this job, whereas right now you have a scientist and coming in and saying what you opened with. What's the value of this? Why should we invest in fundamental science?
And I hope that I was helpful in that regard. Like I said, people who are applying for this grant money are surely more fluent in the quantum that they care about than I could ever be. But to the extent that I could add and help with context, I was delighted to participate. But are people with questions? Is there a way for questions to flow into this?
Yes, there are. So thank you very much, Dr. Roper and Dr. Tyson, for just an awesome and inspiring talk, and so many great things to think about there, especially from our perspective.
Especially manure was the top one.
You went there, I didn't, sir. So we've lined up some special guests, really talking about the next generation here. So I think you're really going to enjoy these questions that we've gotten in the last week or so. And let me just start with the first one. So we have Stephanie Yoshida. She's a senior at Punahou High School in Honolulu, Hawaii. Over the past 3 years, she has been conducting astronomical research on exoplanets, using data from systems such as Kepler, K2, and TESS under the guidance of Dr. Sam Grunblatt. But get this, her work on white dwarf exoplanets has garnered her numerous accolades, such as second place at the Intel International Science and Engineering Fair in Physics and Astronomy category, and second place at the National Junior Science and Humanities Symposium, both in 2019. She intends on pursuing a degree in astronomy or astrophysics in college, where she hopes to keep doing what she's most passionate about, and that's research. Stephanie.
Hi. So my research revolves around finding exoplanets, and as a result, I'm curious about possible extraterrestrial life. And so with humans sending out interstellar messages over the past 5 decades, do you think that mysterious radio signals received by us could indicate possible communication from another life form in the near future? In addition to this, how could accelerating technology help humans find an exoplanet with life?
Excellent. So first, congratulations on your arc of life there. You don't need any help from me, clearly, because you're already in the rocket and the engines are ignited. With regard, let me start your last question first. With regard to best ways of detecting life, if we're not going to life at all, is not necessarily sending us radio waves trying to talk to us. Life could be microbial. And so I think the future of the search for life in our field is the search for biomarkers. So if you have a planet that transits across the face of its host star, then light from that star will actually pass through the atmosphere of the planet before it reaches us. Of course, that signal will be completely dominated by the star itself, but there will be some absorption features that go on here that you can say, oh my gosh, I have found a spectral feature that we know can't exist in the surface of the star because it's too hot. And this feature we know is a product of life as we know it, such as oxygen or methane. So the astrobiologists are today making a list of things for the spectroscopists to look for, which if it's in the atmosphere would be strong indication that something biological is going on the surface. And it reminds me back when I was watching those Star Trek episodes, you ever notice in Star Trek, they never wear spacesuits? You ever think about that? They just beam down to a planet. Now so how does that work? They find a planet that oxygen, nitrogen, atmosphere, captain. Okay, let's just beam down. And it leaving you to think that you just look around until you find one of these planets and then you go there. No. If that planet has oxygen, it means it has life, okay? Because oxygen is highly reactive chemically, and it doesn't stay loose in an atmosphere long unless something is generating it actively. So unless there's some phenomenon that generates free oxygen and it's not biological that we don't yet know about, if you find a planet that has oxygen, you can go there and look for life. And you're a betting person, that's if you to rank planets in sequence of which one you want to visit first, you go there first. That doesn't mean they have radio telescopes beaming to us, but it could mean there's some kind of process where oxygen is a byproduct of the metabolism, which is true, of course, for all plant life on Earth. As far as your first question was with exoplanets, what was the first? I just dealt with the second half.
It was about mysterious radio signals being received by humans.
So here's the thing. So it's cheaper to listen than it is to transmit. So, quote, listen. So we have some dedicated telescopes that are looking up in radio frequencies, studying as many frequencies as possible in the bandwidth that it's sensitive to, seeing if there's some kind of signal that repeats. All right, what good would it be for just one signal? You can't do anything with that. Let's hope that aliens who are intelligent, who have technology, think the same way we do, that you'd want to send something that we can then decode, right? So there's skeptics of this, it's a vast universe and we haven't looked very far, sure. But if you make a discovery there, it is a very high return on an investment that could even start out small. So if there's a budget, you should always, for me, you should always be allocating some percentage of it to make a discovery that could transform all of civilization, such as the discovery of intelligent life in the universe. So yeah, we're still listening. We haven't found anything that's the certain repeated signal, but we're looking. By the way, the more you look, the more exotic is the radio signal you might find, and it could be a natural phenomenon you've just never discovered yet. All right, that's what happened with the discovery of pulsars. We're looking around, and this thing is flashing. Oops, I keep hitting my camera here. The thing is flashing light at us. We say, "Oh, whoa! This is a radio beacon. This is like a lighthouse sending us signals. Oh my gosh, little green men." Okay, and so there was a lot of excitement. So we figured out, no, it was a natural phenomenon. It was a rapidly rotating neutron star with a tipped magnetic field that was spinning out radio pulses. So just keep in mind that just because we don't know what it is, that if we discover something new and don't know what it is, the act of not knowing does not mean it is of alien origin. So anyway, good luck. Sometimes you need a little bit of that too, but we'll see you on the other side.
Thank you.
So we're cognizant of everyone's time, but we're hoping we have time for at least one more question, Dr.
Let's do
Tyson.
one more and I'll just sort of speed up my answer to it. How about that?
Okay, sounds great. Thank you. So we have a question from Laurel Violet White. Laurel is a senior undergraduate studying physics at Syracuse University, where she is both an astronaut scholar and Goldwater scholar, conducting gravitational wave research for the past 3 years. She plans to continue with astrophysics research in graduate school. Over to Laurel.
Hello.
Good morning, Dr. Tyson and Dr. Roper. It's been such a pleasure hearing you both speak. Dr. Tyson, I know you said you can't predict the future, but you were talking about all these like unexplained phenomena that we don't have any understanding of. And I was wondering if you know or have any ideas about what mysteries in science we might be able to solve with a quantum computer.
Yeah, I mean, if you just follow the expectations, the arc of expectations for quantum computing, where there may be certain problems that are completely intractable by classical computing methods that become trivial for a quantum computer, I can be sort of non-imaginative here and say there are systems in the universe where we always have to make approximations, because if we gave the full hammer of what it is we're trying to simulate, it would just take too long. We have clusters of stars, have hundreds of thousands, and in some case, millions of stars, all of them moving simultaneously, everybody feeling each other's gravity, and every tiny movement of one changes the gravitational field of all the others, and they all respond into each other's gravitational field. Those stars were born, they're living out their lives, and they're dying. So we have the gravitational orbits, we have the of each star, we have the collective gravity, we have the stellar evolution calculations, we have all of this that's going on. We have orbit captures if they come too close. Some are spit out. We allow ourselves to make significant approximations on the belief that we're getting our insight into the larger system. So we can do it for 1,000 particles, but maybe not 1,000,000. Okay? If quantum computing allows us to do it for 1,000,000, is there something out there that has 10 million or 100 million or 1 billion? Galaxies have 100 billion stars, all in orbit, forming out of gas. Can we put all that on the computer and then evolve nature in exactly the way nature evolves, and not in some approximation limited by our hardware? If that's the case, then we will have complete knowledge of a system. And it may be, I'm just making this up now, because again, I thought doors would never open when you walk towards them. So here's something we don't really understand. And it's called emergence. You know about emergence? Emergence is, there's a pigeon walking around in the park, and it's pecking its head and it's looking for, and other pigeons, all they're doing their own thing. You could analyze every single molecule of that pigeon, okay? And you can get its metabolism and how it's worked and its evolutionary path. You can get all of that. But it's not going to predict the fact that when the pigeons decide to alight, to ascend from the ground, then they all flock together. Well, how do they know to do that? Could you have figured that out by studying one pigeon? We don't know that. So this is an emergent behavior from the ensemble that is not evident from the individual. And this might be the key to consciousness. Is consciousness emergent? Okay? You can study the neurosynapses of brains and all of this. You say, oh, there's a chemical and it just went this way, and an electrochemical signal, and it does this, and it does this. And it says, can you judge from that this person is contemplating their future, contemplating their death, is studying the history and learn? Can you get that out of just studying the neurosynaptic transmissions in a brain? I don't know that you can, or I don't know that you can yet. It could be that there is a calculation that is still yet to be done, that is way more refined than anything a classical computer has done, that could give us insight into phenomena that to this day remain a bit mysterious and intractable to our classical ways. So That's my answer for you.
Thank you very much.
Thank you, Laurel. And once again, Dr. Tyson, Dr. Roper, thank you so much for your time today. It was a true honor to have you here. I'd like to turn the floor over to you for some wrap-up comments, both of you.
Oh, I don't have I've been, I make sure every comment that I give is like a wrap-up comment because I never know when you're going to end. So,
Neil, we will change the agenda. I mean, we could listen to you talk about
here's what I'll say.
nearly every field of science, and I think that just that speaks to the enthusiasm that the Air Force and Space Force and the nation should have for science, not just because of practical reasons for what it has done to our nation and all nations, but just because of the illusion you made about the car solved the problem. It was not related to the problem it solved in Manhattan, but someone was working on it just merely because it was a new area of research. And with so many areas of physics, we've talked quantum here, but materials are very interesting right now. Nanomaterials, synthetic biology, gene editing. There's so many new things that if I were going back to school now, I might not do string theory a second time, though I do love living in more dimensions than just the four that are common.
Don't complicate.
Yeah.
Don't put me in 11 dimensions or whatever.
The theory does come with strings attached. Literally, in this case, you have to have those extra dimensions, and so you just learn to love them.
Yeah, I get you. I get you. One, I think, an important point here is, I was making a really important point, and then it just escaped my head. See,
it tunneled, Neil.
It tunneled out of my head. Did it tunnel to you?
You got
the thought?
I have not. I'm gonna. Let's see. What could possibly could Neil have been thinking about? I don't think I picked it
really
up.
Good thought too. No, give me a quick second.
Mechanical brain, Dr. Tyson. We have confirmed that here today. I think probably was it something along the lines that we shouldn't just invest because of practical reasons. That a problem that was the automobile solved a sanitation problem on Manhattan. Was being worked on for completely different reasons, but it came in and solved this problem out of left field. And we should always be working on anything that could be new and transformative, gene editing, synthetic biology, nanomaterials, and of course, quantum here today. Any of those could spark a new industrial revolution. So we can't be behind. I don't know which one it'll be.
You triggered it back in me. What I was going to say.
It's like a laser. I have stimulated, I have emitted the photon back.
The wave function collapsed back in my head. So it's you mentioned material science. I just want to say that in my field, astrophysics, we get all the media attention. You know, there's an eclipse, colliding black holes. We had the second student who asked a question specializing in gravitational waves. There was two humongous black holes that collided and was reported, I think, yesterday. So there's all of this. We get headlines. Pluto gets demoted, whatever. There's an eclipse. We get this. The public doesn't see advances in other very important branches of science, some of which are slow, but they work their way into our lives, and you no longer even the moment of announcement isn't there because it happens slowly. For example, I'm old enough to remember, because I think I'm older than you, when anything made of plastic was cheap and it broke. If you bought somebody something made of plastic, that was the end of your relationship, okay? Over the years, plastic just got stronger and stronger and more durable. And then we came up with, transparent plastic, okay? Oh my gosh, you can see through it. These things nobody's thinking about today. Oh, by the way, because it is so durable, it now never leaves the environment, right? So that brought its own problem with it. What I'm saying is that material science is the silent transformer of our world, because this stuff comes out, it gets picked up by engineers, and it becomes product, and all of a sudden you've got a really cool thing you're playing with at home, and you didn't even know it, that some clever engineers enabled it. And by the way, I want to repeat something you said earlier. It's not good enough just to solicit all this. You need to keep a conduit open between the science and the engineering applications to it, because the scientists are not going to come up with those solutions. The engineers are. Some will, but most won't. The engineers will. And that's got to stay open, and there's got to be a funding stream to allow it. Otherwise, no one's going to enter that conduit. And another thing, to echo what you said again, don't ever go up to a scientist and say, how will that ever improve my life? I mean, you could do that, but the scientists, if they're honest, most of the time will say, I have no idea. We get to say that all the time in astrophysics. There's nothing that's going to help put food on your plate. However, I will tell you, bringing this full circle, that my physics professor is Ed Purcell, who discovered nuclear magnetic resonance. You know what his first love is? Molecules in space. Space. All right. He was a part-time astrophysicist and he loved it. And for all you know, his enthusiasm for molecules is what got him to a place where he could say, here's a phenomenon, I think it works, it's nuclear magnetic resonance. So you never know what frontier of research will bring you either the next year, 10 years later, or 50 years later. So all I can do is just endorse whatever frontier research anybody is doing and put it out there. You might have to wait a half a century, but a clever engineer is going to come behind and transform the world, and as a minimum, transform the economy.
And I'm going to get in my rocket ship that is going to be not in horsepower, but something different in future. And
manure power.
Let's get near the speed of light so we can come back and see what the world's like in 50 years. But yeah. Neil, I just want to, on behalf of the Air Force and Space Force, just thank you for so much of your time, your enthusiasm, for making science palpable, real, and important, and most importantly, infectious. And for everyone joining, if you are a researcher, thank you for being here. We are rooting for you. I hope you win. I hope that you bring in that next spooky effect that will eventually, hopefully, become commonplace for us, like the laser is today. For the students that are here, we really welcome you. We are excited about your interest in science, and the Air Force and Space Force are great places to be scientists. We really, really love technology and science in the service, and gauntlet's been laid. So we would like, by this event, that we will continue each year to bring a new quantum phenomena into the military. I don't care what it is. We just want to start making this new battleground of physics something that is as commonplace as the airplane and the satellite is today. So Neil, just want to end by just
forget that. Here's an image. Just don't forget, there was a day when lasers were the size of laboratory rooms. Okay, if you went back then with your pocket laser and showed it to them, and they say, "Where'd you get that?" I say, "Oh, at the it was an impulse item at the checkout line at Kmart." Okay. What the hell happened? Okay. That's how this works. Okay. That's all I'm saying.
Neil, thank you again. And I'll turn back over to our research lab.
Everyone keep looking up. Excellent.
Everyone have a great event today.
Thank you.
Thank you so much once again, Dr. Tyson and Dr. Roper, for all your time today and this awesome talk and just inspiring conversation.